In the last class, we started our discussion about processes that evolve over networks, and we saw diffusion as our first example. We're going to talk today about infection models on networks, and to be honest, there's quite a bit of work that has used diffusion as a way to model the spread of a disease. However, there are some unique characteristics to modeling infections, and so that motivates us to consider a more specific model. These models, although we call them infection models, and we'll talk very much about kind of the spread of a disease, it's certainly possible to use similar approaches to model the spread of an idea. We even use the term that an idea can be infectious. We can talk about characteristics that would affect voting or election. We can talk about characteristics that would represent how people think about products and their buying behaviors. So although we talk about diseases, these models can be thought of in a larger umbrella. And so before we get to the network context, there's a lot of work that is at the population level, and this allows us to better understand kind of some of the dynamics that we'll see in the network models. So we're going to start off talking about the population level models, which represent the entire population as a whole without considering individual connectivity. So there is no network in this context. We call this an SI model because it includes people that can either be susceptible, that's another word for being healthy, or they can be infected or sick. And so what we're going to use is we're going to use a state that represents the fraction of people infected. And so again, remember, we're not talking about a network, so X is really just a single number. In this case, it's a fraction, so it's between 0 and 1. And that represent how many, or the fraction of people in the population you're considering that are sick. And so that means that the rest of the population is going to be healthy. And so typically we start at a reasonably healthy population with a few sick people, and then we see how the infection spreads. And so we are going to consider the simplest model that could represent the kinds of behavior that we want to illustrate in terms of sick people infecting healthy people. And the idea is that we're going to represent this as a differential equation, and the rate of change of the sick population, so how many more people become sick, that's going to be a function of how much the sick people intermix with the healthy people. And so this assumes, all population models assume a relatively well-mixed population. So that means that essentially the sick people are constantly moving around and have exposure to all of the healthy people. And so there's kind of a uniform level of infection. So even if there's just one person, we kind of assume that's sick, we kind of assume that they can get around and on average touch everybody. So in the spirit of this well-mixed model, the idea is that the more sick people we have, the faster we're going to have sick people becoming sick. So the rate of change is going to become greater if the number of sick people is high. At the same time, once you get close to a completely infected population, it's also going to slow this rate down. And so that means that there needs to be a factor that counterbalances that. The idea that you start running out of people to infect, and so fewer and fewer are going to become infected. And so one of the ways of capturing that is by multiplying by the number of susceptible people. So essentially, when the disease is first starting, this X is a small number, and this is a large number, so that's close to 1. And so that starts to drive this derivative higher and higher. And then once X becomes large enough, now 1 minus X becomes relatively small. And this leads to slower rates of change. And so this is, again, probably the simplest model that you could probably use to describe this. And there's certainly more sophisticated tools and expressions. But what we want to do is be able to understand how this kind of mixing then affects the derivative. And so an important factor here is this beta term. And so we're going to call that the infection rate. And so that is essentially how infectious the disease is. So something that spreads quickly from person to person would have a high beta. Something that needs very close contact or prolonged contact spreads very slowly, it would have a low beta. You can kind of think of, again, about this beta as being a little bit of that viscosity term that we talked about in the diffusion models. So because this is a differential equation with really only one variable, x, we can separate it and we can solve for an analytic solution. And it'll look something like this. And so when people talk about logistic growth, this is the kind of model that gives rise to that, so this product. And so you'll see things, if you remember your predator-prey relationship, this is also the kind of model that we use to represent predator and prey models, in the sense that essentially the number of, say, wolves increases if there's many prey available. But if there aren't a lot of prey available, then you're not going to see great growth in the predator population. So again, logistic growth is found in a lot of different places, and so we see that come out of the SI models. But this model is certainly missing something, and it's missing the fact that people can recover, and so that's what our next model will take into account. Before we get to the SIR model, it's useful to kind of think about the SI model from as a system of two equations with two unknowns, even though in fact we can rewrite this as a single differential equation. So one of the ways that we can do that is we can introduce a new variable called S, and that's going to be this fraction of people that are not infected, so those are the susceptible people. And so now we're going to have our same differential equation that we had before. This is what we had before on the previous slide, where S was essentially 1 minus x. And now what we're going to do is we're also going to model how S changes. And so that's going to change. Essentially, people from the susceptible population move to the infected population. And so that means that when they make this move, essentially when they become infected, you're moving people from the susceptible population to the infected. So everyone that you add to this equation needs to be removed from this population. So even though we're talking about fractions, the same idea of conservation here makes sense. And so that means that the amount that x increases must be removed from s. And again, this is this whole idea that essentially x plus s has to be the entire population, or 1. So by looking at these as the system of equations, we can now move one more step towards the SIR model and introduce our next term a little bit easier. The SIR model, where the R represents recovered or possibly removed, depending on whether you're a pessimist or an optimist, essentially R represents people that are no longer part of the infectious spread. And so this could be because people that are sick recover and now they have an immunity to the disease. So that happens oftentimes with viral diseases. So if the patient recovers, then they no longer are susceptible any longer. And so that's why they don't go back into the susceptible pool. It's also possible that that could model, or something similar to that could model, a death rate as well. It is possible to have what they call an SIS model, which is susceptible, infected, susceptible, which means that now the people that are recovering are again susceptible. So there are some diseases that people can get again and again. And there's a variety of other different permutations, SIR, SIRS, SIS, and so there's even more variance beyond that. But we'll stick to these models. So as we want to represent the recovered population, this again is going to be quantified by a recovery rate, which I'm going to use this term gamma. And again, it makes sense that the simplest model is simply that people recover at a given rate. And so this means that this is the change in the recovered population, where the recovered population is the variable R. And so that they're going to recover at a rate that's proportional to this gamma. Now remember that this is a flow from the infected population to the recovered population, and so that means that these terms are equal and opposite, just like these terms were equal and opposite. And so in combined, again, x plus s plus r has to be the entire population 1. Once we've introduced now this system of equations, and this now really has to be a system of equations. It could be a system of equations of just two variables, but it becomes useful to represent it in these three variables just for clarity. It's difficult to come up with an analytic solution, and so now we have to integrate these numerically. But the types of responses that we would imagine look like this plot, where we have originally a large susceptible population that essentially ends up getting smaller, and the infected population rises and then falls, and then the recovered population grows. And so a very interesting question then is essentially, what part of the population is going to be affected by the disease? And in terms of, you can see that over a long period of time, once you go far enough out on this time axis, there are no longer going to be any more infected people, because either everyone's been infected or people haven't. And so the question is then, in the long time behavior, what is this R recovered population doing? Is it approximately equal to 1? Or is it something that hasn't affected the entire population? And so that's a key question in understanding whether this kind of population level SIR model captures an epidemic where it affects a large part of the population, or whether it's something that only affects a smaller fraction. So to answer this question about long time behavior, we're going to try to capture what exactly is going on with this recovered population as time gets larger and larger. So the rate of change of the recovered population was gamma times x, the infected population. We can write x using this conservation law. We can write x in terms of 1 minus s minus r. So now we've reduced the number of, we're starting to reduce the number of variables involved in this calculation. So now we've got these two parameters, s and r, and so it's difficult to figure out anything analytically if we have these two variables. And so what we're going to do over here is we're going to try to figure out what s looks like, what the healthy population looks like over time. And so if we look at our these two equations here, we can see that there is a common x term, the fraction of infected people. And if we set these two equations equal to each other, we can see we get an equation in S and an equation in R. And if we go ahead and separate these equations, you get down to the point where you get this exponential differential equation again, or the differential equation that leads to an exponential behavior like this, where this beta over gamma is the infection rate over the recovery rate. And so now this is an interesting equation, because now this R is not, S is being captured as a function of R, but this becomes useful once we plug it in over here. This allows us now to have an equation that's only based in R. And so if we expand this out, we're essentially looking for long time behavior. So we're looking for when the derivative is equal to 0. And so that happens, we get this condition down here. And this little thought bubble here is saying that, well, this looks a lot like the giant component expression that we had before. Essentially, we had this relationship that we had to numerically solve, where R was going to be equal to 1 minus e to this constant times R. And so because this initial population that is healthy, S sub 0, is usually about 1, then this really does look a lot like this giant component. And so now you can imagine, if you remember, we had on the x-axis, we had C, and then essentially there was an average degree of 1 where the giant component emerged. And so in the context of the infection models, this is saying that essentially for a low enough, now we're going to get rid of C and we're going to replace it with beta over gamma. For a low enough beta over gamma, essentially lower than 1, you're not going to see a very large R of t. Essentially, you're not going to have a lot of recovered people, which means you didn't have a lot of infected people. But once beta over gamma becomes larger than 1, now quickly you get this emergence of a large recovered population, which means that it has infected a large part of the population. And so then this becomes what's called the epidemic threshold, where this beta over gamma is equal to 1. And so this kind of makes sense in the sense that you have beta representing how quickly the disease is infectious, how much the disease is infectious, and then gamma is related to the recovery rate. So if people recover really fast, then gamma will win, and that fraction will be, or that number, this epidemic threshold will be less than, sorry, the number beta over gamma will actually be less than 1, the epidemic threshold. But if beta, if it's really infectious compared to the recovery rate, then you will definitely have this epidemic because it's beyond this epidemic threshold. One of the criticisms of the SIR model is that it doesn't model the recovery very well compared to what we know in practice. So to take a look at that, we look at trying to quantify the probability that someone is still infected after a given amount of time, that given amount of time being tau. So the book goes through this calculation where essentially it chops up that tau amount of time into smaller delta taus, and the probability of recovering at any delta tau is this gamma times delta tau. So it's essentially the recovery rate times the amount of time. So that if the amount of time is delta tau, then you multiply by that by gamma, and that gives you the probability of recovering. So the probability of not recovering in delta time is 1 minus gamma times dt, delta tau, so this quantity. So that's essentially not recovering in the first delta tau. Then this is not recovering in the second chunk of delta tau. And then we have to have tau over delta tau, many of these delta tau intervals. So we're going to have this tiny interval that's measured by delta tau, and then we're going to have a whole bunch of those, and how many we have is this tau over delta tau. And so essentially we're looking at a probability that is computed like this as you let delta tau go to 0. And so this is an expansion formula for the exponential, and gamma is the rate, or minus gamma is the rate of that exponential. So what that means is as the time goes by, the amount of people, the probability that you would be recovering from being infected would look like this exponential. But we know that in practice, people recover essentially in a more bell-shaped fashion around some nominal time. So for example, like the flu, you may recover in about a week, but some people recover a little faster, a little bit slower. And so this exponential distribution doesn't exactly model that particularly well. Nonetheless, it is still a very usable model for quantifying spread over populations, and what we'll see next is talking about spread through networks. So if that's the probability, if this is the probability of not recovering after tau, then the question is, if we've waited tau amount of time and then you happen to recover in the next delta tau, then the probability of doing that is simply just essentially not recovering for tau time, and then going ahead and recovering, that's the gamma times delta tau that we had, and that's recovering in that next delta tau. So that is our probability of recovering exactly between tau and tau plus delta tau. And so we're going to use that in just a second. One of the ways that people talk about the spread of a disease is through this reproduction number, R sub 0 or R naught. And so this is essentially, the way they define it is the average number of people an infected person will then pass the disease on to. And so it's intuitive then, if each person passes the disease only on to one other person, then essentially the number of people that are infected kind of stays constant. If R naught is less than 1, then the disease inherently doesn't spread. Whereas if R naught is greater than 1, then the disease does spread. So most diseases that we'll experience have R naught values greater than 1, but it's interesting to kind of think about R naught values less than 1 in the context of these other applications, like in voting or product adoption, and trying to figure out how one could still manage to influence a large population despite having a relatively low R naught value. So the way to calculate R naught, one of the ways to calculate that, it's kind of intuitive once you get to the answer, but is to say that suppose someone stays infected for time tau, which sounds a lot like what we did on the last slide. So if someone stays infected, which means that they are, say, infectious over that period of time, if we assume that we're close to the start of the disease where there's plenty of people to infect, so S is equal to about 1, then the number of people that we would expect to be infected would be beta, the infection rate, times tau. And this simply just comes from the fact that S is equal to 1. So the beta times S times tau just becomes beta tau. And so if we put that, so that's the number of people that are expected to be infected, multiplied by the distribution of essentially people being infected for time tau and then recovering at time tau plus delta tau. That's this quantity. And we integrate all over the different tau possible recovery times. Then what we get is out pops beta over gamma, which is that same epidemic threshold. And again, it makes sense that we said that this being greater than 1 indicates an epidemic, and less than 1 indicates not an epidemic, so it's not spreading. And so that gets back to this R naught value. So it's interesting to see how our epidemic threshold that we got from our prior calculation really connects with the definition here of the R naught. So next we'll move on to looking at the networked version of the SI and SIR models for infection.